For the past year, we've been exploring how dependent types can be used to reason with and represent natural language statements.
Martin-Loff type theory is a system of logic where propositions correspond to types. In this framework, writing a program corresponds to a constructive proof by virtue of the type checker. Moreover, proofs become mathematical objects with a rich intrinsic structure.
Montague was the first to show how natural language follows a strict formal structure similar to programming languages. Recent research by Ransett and Cooper has shown how types can enrich linguistic translation. But what if we can exploit the formal structure of natural language to enable type-theoretic reasoning?
We propose a novel methodology to translate natural language into a type-theoretic representation. Within this encoding, we synthesize relational proofs between natural language statements. Moreover, we explore both reasoning over epistemic modalities and the use of interpretation mapping to understand proof objects.
If Socrates is a man and every man is mortal, then can we make explicit the proof that Socrates is mortal? The combinatory categorical grammar assigns each word a syntactic type, then derives a tree-like structure through combinatory rules, similarly to a parse tree.
We define a homomorphism between CCG derivations to the lambda calculus. We map syntactic types to lambda constructs with wider application order matching that in the original CCG tree. This augmentation preserves the content while adhering to the grammatical structure. The term generated by this derivation reduces to the compositional logical form of the sentence.
We define a function mapping the logical form of sentences to their record constructions. Its relations are a special case. The system encodes Socrates as a man as a bundle containing an entity alongside dependent proofs that said entity is both Socrates and a man.
The other premise, every man is mortal, is encoded as a dependent function, taking evidence of being a man to evidence of mortality. Lastly, the hypothesis, Socrates is mortal, is encoded as a bundle, similarly to Socrates is a man. Then the system generates a corresponding actor file. Within this encoding, an empty theorem is created asking if the conclusions can be constructed from the premises. This is defined as a whole, before a proof is synthesized using AGSI.
Since the proof object is highly structured, it makes explicit the mechanical intricacies of the entailment. It's possible to reverse engineer this proof object to obtain a natural language explanation. On the forward translation, we map records and their fields to their interpretations.
Once synthesized, we parse and interpret generated proofs using this mapping. By traversing the AST, we can generate a natural language counterpart to the original proof object.
This symbolic interpretation is trustworthy and accessible.
We implement this methodology as a fun, friendly theorem prover that generates literate actor proofs with generated natural language explanations. Moreover, it renders diagrammatic representations to the user.
This makes theorem proving more accessible by lowering syntactic barriers to entry.
We're proud to announce that we've both achieved our goals and even had time to include additional modal axioms.
Above all, our favourite discovery was the reverse translation of the Curry-Howard correspondence to yield natural language proofs.
Thanks for watching.